Hi guys, Mohit here. And in the last video, we learned how Torch Dynamo captures a regular Python program while it's executing. And instead of trying to optimize Python directly, it observes every tensor operation and records them into something called an FX graph. But that raises another question. What exactly is an FX graph and what information does it contain and why is it so important that every later compiler stage depends on it? That's exactly what we are going to understand in this video. An FX graph is simply another representation of your model. Instead of storing Python statements, it stores the tensor operations that your model performs and the relationships between those operations. Okay, so you can think of it as a graph that describes how data flows through your model from input to output. Let's take a simple model as an example. Suppose we have a linear layer followed by a ReLU activation and followed by another linear layer. Even though we wrote this as a regular Python code, the FX graph represents each of these tensors operation as a individual nodes connected together. Every node represents one operation and the arrows between them represent data dependencies. In other words, the output from one operation becomes the input to the next. This gives the compiler much cleaner picture of the computation rather than the original Python ever could. Now let's look at real FX graph actually looks like. If you look closely, you will see that every uh, node represents the same kind of operation. Not every node has the same kind of operation. A placeholder node represents an input of the graph, for example. A call module node calling and .nn dot module like linear or layer norm. A call function node represents a regular Python function such as torch.relu. A call method node represents methods that are directly on tensors like view or reshape. And finally, every graph ends with an output node that returns the final result. Together, these nodes types are enough to describe the entire computation happening inside your model. Now we have our FX graph. At this point, the Torch Dynamo's job is basically complete. It has watched your Python program execute, captured all the tensor operation and represent them into an FX graph. But if you think about it, the graph itself doesn't make your model faster. An FX graph is simply representation of the computation. It tells us what operations exist and how they depend on each other. That's it. But someone still has to optimize the computation and generate efficient code, right? That's exactly where TorchInductor comes in, and that's what we'll discuss in the next video. We will open up TorchInductor itself and see how it takes this FX graph, applies compiler optimization, and finally generates the Triton and C++ kernels that power torch.compile. Thank you for watching, and I will see you in the next video.